Okay, so last time we gave this general procedure for plumbing fixture in the case of superstring, okay, but it was perhaps somewhat abstract. So let me illustrate this by an example today, okay, and how exactly it works of plumbing fixture. Fixture in the Riemann sector. Okay, because that's where the subtlety is. Okay. So let's take a torus with two Riemann punctures. So this is R. This is also going to be an R with, so these have minus half picture number, okay, because that's the prescription. And take another surface which will take to be a sphere with four punctures. These will be taken to be NS. So these are in the -1 picture. This will be in the Riemann, which is in the -half picture. And this will be in the Riemann, which is -half picture. Okay. And now let's also put in the picture changing operators. Okay. So let me remind you the number of picture changing operators. So number of PCOs is 2G minus 2 plus M plus N by 2, where M is the number of Nebel-Schwarz sector and N is the number of Riemann sector vortex operators. Okay. So here we have G equal to 1, okay, and M is 0, N is 2. Okay. So that we need a 1 PCO. Okay, so I'll denote by PCO these crosses with circle crosses. Okay. Here, let's see, we have altogether G is 0. Okay, so -2, and then you have 2 Nebel-Schwarz, so that's +2, and you have 2 Riemann, so that's +1. So again, we need 1 PCO here. Let's call this. So this is a PCO. Okay. And now, of course, everything matches. Okay. Now, when you do the plumbing fixture, that means when you join these by a Feynman diagram, by a propagator, okay, what you are supposed to do is to take some mod W equal to mod Q to the half surface here, okay, and then you take another mod W prime equal to mod Q to the half surface here, okay, and then identify them using W prime equal to -Q. Okay. And from what I told you last time is that you have to also insert a picture changing operator integrated. Okay, so let me write that down. Okay. So we have, so once you join these two, okay, what do you get? We get something like this. So here you have one Riemann, which is -half. Okay. Here you have 2 NS. Okay. One Riemann, which is -half. Okay. And then 1 PCO on each of these. Okay. And what I told you last time, okay, from that it follows that on this neck, okay, you have to insert a PCO, but not at a single point, okay, but as an average over many insertions. Okay, and that averaging was precisely integral dW over W times chi W. Okay, so that was the content of what I told you last time. Okay, and the reason that you have to insert it is because it's a Riemann function. Okay. So now let's see that the PCO counting works correctly. Okay. So this new surface, okay, has genus 1. So you have G equal to 1. Okay. How many NS punctures? There are 2 NS punctures. So M equal to 2. Okay. And we have 2 Riemann punctures because 1 here and 1 here. So N equal to 2. Okay. So we need 2G minus 2 plus M plus N by 2. Okay. That's 2 plus 1, 2 plus 2 by 2. That's 3. Okay. So you see that on this surface, you need 3 PCOs. Okay. So it was essential that you have to insert this chi0. Okay, we have to insert an extra chi somewhere. Okay, because the PCOs which are inserted on the original 2 Riemann surfaces, they are not enough to make up for the total PCO that is needed on the glued surface. Okay, and this is a prescription that you put the PCO on this as an average. Okay. You can easily convince yourself that instead of having Riemann puncture, if you had NS puncture, okay, we can do a similar analysis, and there you will not need any PCO on the neck. Okay, the numbers will add up exactly to match what you need. Okay. So it's only for the Riemann puncture that you need the PCO. Is this clear? Are there questions? Okay, now let me address this infinite degeneracy problem that I had mentioned earlier. Okay, so I'll explain it again. So suppose you have a plumbing fixture with Riemann. Okay, so what we said is that we have to insert this. So we have phi r of 0, phi s of 0. Okay. And then we have, let me write in the correct order. It doesn't really matter that much. This is just a matter of sign. I think this is the order I have been following. Then you have q to the hs, q bar to the hs bar. Okay. And you have to integrate over mod q less than or equal to 1 with the measure dqh dq bar. Okay. Now, what was the problem that I had mentioned earlier? Okay. So these are in minus half picture. Okay. These are p equal to minus half, and from there it follows that these have picture number minus 3 half and minus 3 half. Okay. Now you can easily convince yourself, and this I'm leaving as an exercise, okay, that beta 0 acting on minus 3 half, okay, with some momentum k is not 0. Okay, this follows from the kind of analysis that I did earlier. Okay, and for gamma 0, it's the other way. For gamma 0 acting on minus half k is not 0. Okay. So this means that if you are trying to build a basis of states in the minus 3 half picture number, okay, we can take beta 0 to the power n times minus 3 half k. Okay. This is degenerate with minus 3 half k for any k, for any n. K is just there for keeping the track of the momentum, or otherwise it's not going to play any role. Okay, so this means that you have infinite degeneracy, infinite L0 eigenvalue, and that means that however much large n you take, these things don't get suppressed. Okay, because it remains the same power of Hs. Similarly, here, okay, I could have replaced this Hs by Hr, right? Because they have the same conformal limit. Okay. Similarly, instead of phi sc, we can take minus 3 half k with beta 0 to the m. This is again degenerate with minus 3 half. Okay. So this a priori has a problem that we have infinite degeneracy of basis states, which do not get suppressed. So if you try to sum over R and S, okay, you may run into divergence. However, in this case, you can convince yourself that the divergence doesn't arise. Okay? And the reason is the following. Okay? You see, when you take this object, okay, this has Gauss number minus n. Okay? Similarly, this object has Gauss number minus n. So if you create states by beta 0, okay, then the Gauss numbers are reducing. Okay. But of course, you know that on a sphere, so this is the sphere correlation function. Okay. On a sphere, the total Gauss number has to add up to 3 plus 3. Okay, 3 from the holomorphic, 3 from the anti-holomorphic sector. Okay. So if you try to reduce, if you try to pick basis states for which the Gauss numbers are arbitrarily large and negative, they cannot get non-zero matrix element. Okay. So the matrix element will vanish. This implies that the matrix element vanishes unless compensated by positive Gauss number operators. Okay. So how can we build positive Gauss number? Okay. Gamma 0 is not useful because gamma 0 annihilates this. Okay, minus 3 half k is annihilated by gamma 0. Okay. We can use, of course, gamma minus 1, gamma minus 2, etc., but those raise the L0 eigenvalues. Okay. So those are not going to give divergence. Okay. So gamma is not useful. So gamma n minus n not useful. Okay. The other thing which carries Gauss number is C or C bar. Okay. So you can use C1 and C0. Okay. C1 lowers the L0 eigenvalue. Okay. C0 keeps it unchanged. Okay. But because these are Grassmann odd, okay, these can be applied only at most once each. Okay. So you cannot use this to compensate for arbitrary number of beta zeros. Okay. So this limits the number of beta zeros you can add. You can, of course, add C minus 1, C minus 2, etc. Okay. But these again raise the L0 eigenvalues. Okay. So again, these are not very useful. Okay. So because of this, we see that even though the basis states can have infinite degeneracy, okay, once you have written a sum like this, okay, this doesn't suffer from that problem. Okay, because those infinite number of degenerate basis states don't actually contribute to this sum. Is this point clear? Okay. And now I'll try to show why chi0 is crucial. Okay. Suppose we didn't have chi0 and we are dealing with something like this. Phi r of 0, phi s of 0. Okay. And then you had phi r c. Phi, it doesn't matter. B0, B0 bar, phi sc, q to the hr, q bar to the hr. Okay, I've just exchanged r and a, yes, but it doesn't really matter. Okay. So now, total Gauss number here has to add up to minus 2. Okay. So if you, sorry, total picture number. Okay. So if you take this to be in the minus half picture, okay, then this must be in the minus 3 half picture. Okay. If this is minus half, then that means this must be minus 3 half. Okay. and this is minus half. Now let's see what happens. Now here, as usual, as before, this is minus 3 half. So we can take minus 3 half k acting on beta naught to the m. This is a minus half picture, and on this the gamma 0 is not non-zero. Okay, so this is another exercise. Gamma 0 on minus half k is non-zero. So for this we can now build basis states by taking gamma 0 to the power m on minus half k. And now you see that there's no problem with ghost number, because beta 0 ghost number can compensate for gamma 0 ghost number. So now we would have arbitrary number of basis states, all of which have the same h. This doesn't change, and all of which contribute. Beta 0 to the m, gamma 0 to the m certainly does contribute. And you can easily evaluate this because you can pass beta 0 through gamma 0 by picking up the commutator. And then beta 0 will annihilate this. And this way you can figure out what it should be. And this gives divergence sum. So this also shows why this Feynman diagram way of organizing the amplitude is a useful thing. Because once you use this Feynman diagram approach, and assign that the Riemann sector states must have host number minus, must have picture number minus half, then you don't have a choice of making this into minus 3 half. These have to be minus half, which means these have to be minus 3 half. And so you have to insert an extra operator which I have taken to be chi0. So this means that in the Riemann sector, in the R sector, the propagator, remember we had done the NS sector propagator by integrating over the Q, and there it was phi RC, B0 bar, and then you had a delta L0 bar, and then 2 over L0 plus L0 bar. I think we had something like this. No, I think propagator we had 1 over L0 plus L0 bar. Sorry. Or did you have a 2? Maybe we had a 2 because dq was dq bar give a 2. And it doesn't matter, I'll leave this to you to figure this out. But now what we have is an extra insertions of chi0. And this is perhaps not so surprising because you are probably familiar with the fact that Dirac propagators is not 1 over p square, but it's p slash minus m over p square plus m square. So this chi0 plays the role of this p slash minus m because these are fermionic states. This plays the role of p slash minus m in the, or p slash plus m, it depends on your convention, in the numerator of Dirac propagator. Other questions? So now I'm going to turn to the last topic. And this will take some time to discuss. And that's the topic of spurious poles. Now for this, let's recall that in bosonic string theory, all divergences come from q goes to 0 limit of some plumbing fixture variable. So these can be treated via Feynman diagrams. By regarding the amplitude, this we have already discussed in detail as sum of Feynman diagrams. Okay. And these, of course, can also be done for superstrings, as we discussed. Okay. So these kinds of divergences we can deal with by regarding the sum of Feynman diagrams. Okay. But what happens in superstring or heterotic string? The integrand has additional poles. Okay. And these are known as spurious poles. Okay. Physically, one can show, okay, that these arise from breakdown of gauge choice for local world sheet supersymmetry. Okay, remember that we had a world sheet supersymmetry which we had to fix. Okay. And those essentially introduced all these complications of beta gamma picture changing operators, etc. Okay. So these spurious poles occur when the local world sheet supersymmetry gauge choice breaks down. Okay. And these cannot be dealt with using Feynman diagrams. Okay. These cannot be dealt with using Feynman diagrams. Cannot be dealt with okay. So we will now describe how where they come from and how we deal with this. So let me just give some example first. What kind of pole are you talking about? Okay. One class of examples come when two picture changing operators collide. Okay. So in PGMN, okay, the choice of a section specifies choice of picture changing operators, and it may happen that two picture changing operators are taken at the same position. This gives singularity since chi of y, chi of z goes to infinity as y goes to z. Okay, this is an exercise. Check this. The second come from where the picture changing operators approach the location of a vortex operator. Okay. So I'll write this as y alpha goes to 0 in the WA coordinate. Okay. Remember that in WA coordinate, the puncture is at WA equal to 0. Okay. And so if you take the y alpha inside a disk dA and take it to 0, okay, that's again causes divergence typically, okay, at least for off-shell external states. And that's again something you have to deal with. Okay. There is another surprising class of singularities, okay, that on surfaces of genus 1 or higher, that means torus or higher, when you write down the expression for the xi eta phi correlation function, have poles at points where no operators collide. Okay. These are perhaps the most surprising kind. Okay. Doesn't follow the usual intuition of conformal field theory. Okay. And that essentially is a reflection of the fact that this di eta phi CFT is not really a proper CFT. There are various subtleties with this, right? One subtlety you already saw, this unbounded from below spectrum. Okay, that's not unrelated to this feature. Okay. And the reason that we know this is because we know explicitly the form of the correlation function. So I'll not write down the form of the correlation function, okay, but let me give the reference. Okay. So this is Verlinde and Verlinde. This is physics letters B. This is old paper, 192, page 95. Okay. And the general structure of this, the places where this happens, okay, for the case of interest, okay, is that there is some functional relationship involving the locations of the PCOs, okay, and the moduli. Okay, when that vanishes, this happens, and this function is constructed in terms of the higher genus theta functions. Okay, so it's not a very unusual function, but nevertheless, the fact that there are poles at this when this is satisfied is somewhat unusual. It doesn't happen for usual regular CFTs. Okay. So here, these are as usual PCO locations, and these are the parameters of the moduli space of M GMN. Okay, which means that it contains the parameters of the Riemann surface as well as the locations of the punctures. Okay. So all these can be summarized by saying that in PGMN, there are codimension 2 subspaces on which the spurious poles are located. Well, maybe I should write it rather. Okay. Not that somewhere in the subspace there is a spurious pole. Okay. The spurious pole location, locus basically lies along a codimensional 2 subspaces, okay, along which the spurious pole loci lie. Okay. So why codimension 2? Okay, so let me explain that. Okay. So suppose we introduce again the coordinates of P PGMN. Okay. And now let's look at the various conditions that we had, various kinds of spurious poles. Okay. So the first kind was y alpha equal to y beta, but now on P, of course, y alphas have to be thought of as functions of T, right? So once you specify T, everything else is fixed. Okay. Locations of the picture changing operators, the moduli, the local coordinate choice, etc. Okay. So I should write this as y alpha, sorry, y minus y beta t equal to 0. Okay. This is two conditions, because you have real part and imaginary part. It's a complex equation, right? So it's real part and imaginary part has to vanish. So two conditions. So that's codimension 2. The second class had y alpha of t equal to 0. Okay. Again, two conditions. Okay. And the third class had this form, the complicated function, but nevertheless, okay, I can write this Okay, so this is a complex function. So again, you have real and imaginary part. Okay, so again, two conditions. Okay. And now the problem is that you have to now choose a section in PGMN and integrate the integrand over that section. But typically what will happen is that if you choose a section SGMN will intersect the spurious pole loci on codimension 2 subspaces. Okay. So on this codimension 2 subspaces, the integrand becomes singular. And it's not clear how to integrate. Okay, it may become ambiguous, it may become infinite. So this is something you have to deal with. Okay, so I'm now going to describe this by drawing a figure. Okay, but of course I cannot draw a multi-dimensional figure. So I have to take a simplified approach. Okay, so I'll draw one fiber coordinate in PGMN, okay, which will be the location of some PCO. Okay, and then I'll draw a two-dimensional base, okay, which will be which will represent MGMN. Okay, so let me take this simplified picture of the. So this is a fiber Y alpha, okay, and a two-dimensional base MGMN. This is just a representative picture. Okay. And now the spurious pole locus is a codimension 2 subspace. There may be multiple one of them. Okay, but let's just draw one. So let's take draw a codimensional 2, codimension 1 subspace in this 3 dimension, right? That's a line. Okay. And now we have to draw a section, right, of MGMN. So let's try to draw a section. Okay, it of course goes. So let me make this figure a little clearer. So at some point, what's going to happen is that this spurious pole, okay, is going to intersect this locus. This is a one-dimensional line. This is a two-dimensional subspace. So it's going to intersect at some point, right? So let's call that intersection. Okay, let's draw it here, or maybe here. Let's suppose it has intersected here. Okay, so then the rest of the line is below. So let me just draw it like this. Okay, just to indicate that this goes below the subspace, below the section, and then it goes up. So the problem is to integrate around this region. Okay, and the question is how do you integrate about this region? So let's call this S. This is SGMN. Okay, so now I'm going to describe how we go about integrating over this subspaces like this. Okay, so you have to basically, the idea is that you have to change the section. So we cannot work with this section. Okay, there is a special class of sections, okay, for which we can do this integral. Okay, and those are the class of sections that we'll be working with. Okay, so we first cut out a small region around this point where it intersects, a small region on the section on SGMN. Okay, so let's say this. Okay. Then we are going to erect a vertical cylinder. on this, so that the cylinder passes through the spurious pole locus, okay, and after that you can close it up. Okay. So then let me say what the choice of section will be. What is the surface on which you will be integrating? Okay. So first of all, we take the part of SGMN that is outside this circle. Okay. So let me try to draw this. Okay. So you include everything, but not the interior. Okay. So let's call that S tilde GMN. Okay. Then we also include this disk-like object here. This one, let's call this S hat GMN. Okay. And finally, we include the cylinder. Okay, let's call this C. Okay, we call this C. So we integrate. So the prescription is that we will integrate so this flow closes, of course. Okay. We have just deformed the section, okay, by adding this vertical segment and then closing it off after you have crossed the PCO. Now, from this figure, it should be clear that S tilde doesn't intersect the spurious pole. Okay. Neither does S hat. S hat is here. Okay, it doesn't. So these integrals don't have problem. Okay. But the cylinder does. Okay. And it's not surprising, right? Because there is a topological obstruction. Because the spurious pole was crossing the section, so you couldn't possibly deform it and not hit the spurious pole at all, right? It's a codimension 2 singularity, and you have to deal with it. Okay. But all you have done here is that this codimension 2 singularity, okay, is being encountered on this vertical cylinder. Okay. And we will see why this is helpful. Are there questions? Is this clear? Okay, so let me now draw the vertical cylinder. And the spurious pole enters the cylinder at some point, then goes through, and it emerges below. Okay, so this is a point of the problematic point, right? We are integrating over the surface of the cylinder, and on the surface there's a pole lying here. Okay. Now, what is special about this vertical direction? Okay, and that's what will help us get around the problem with spurious poles. That along the vertical direction, only the coordinate y alpha of a PCO varies. Nothing else changes. Local coordinates remain fixed. The coordinates of all the other PCOs remain fixed. Okay, so the Fs of tau s, right? I mean, remember that. So this Fs, this remains fixed. Then y beta for beta not equal to alpha, okay, all these remain fixed. Okay, so let's denote by t the coordinate along the vertical direction. Okay. And the idea is that we are going to do the integration along the t integration first, okay, the vertical direction, and then we will integrate over the rest. Okay, this circle, okay, which is the orthogonal direction of the cylinder. So to do this, you have to find the t dependence of the integrand. Okay. Now, as we can see that the t dependence is essentially coming because y alpha depends on t, nothing else depends on t. Okay, so let's compute. Okay, so let's first calculate bt. For every coordinate there is a b, right? So let's compute bt because this is what is to be inserted. Okay. So this is, let me write the general definition first. Integral over cs del fs del t b sigma s d sigma s plus sum over s integral cs del fs bar del t b bar sigma bar s d sigma bar s, okay, and then minus sum over beta 1 over chi y beta del y beta del t del xi y beta. Okay, these are the form of pt. This in this case only gets only one contribution, that's when the beta equal to alpha. Okay, this becomes minus 1 over chi y alpha. Okay, so this is bt. We are now going to collect all the t dependent terms inside the correlation function. So you have to do this integral dt, okay, then bt, okay, and the various other things. Okay, so what are these various other things? Okay, so this, let me write the expression for bt first. So integral dt. So here you saw we had minus 1 over chi y alpha del y alpha del t del xi y alpha. Okay. Then these various other things are the other bt's. Okay. But these do not depend on t because the y alpha dependence has gone away. Okay, so these do not depend on t at all. Okay. Then you have product over beta, chi y beta, okay, and then the vortex operators, product over vi, product over wi. Okay. So here, what I can do is that I can just cancel this chi y alpha and write it as beta not equal to alpha. Okay. So let's do that. Let's cancel this and write this as beta not equal to alpha. Okay. So then there is no t dependence from here because y alpha has gone away. Okay. And now you see that the t integral can be done. Okay, because this is the entire content. So t integral basically comes from this part. This is the only part that depends on t. Okay. So what do you get? Okay. This is the ddt of xi y alpha of t. Okay. So what you get is that you get xi of y alpha 1 minus xi of y alpha 2, and then the rest, product over bti, product over beta not equal to alpha, chi y beta, product over pi, product over wi. Okay, and then the rest of the integrals. Okay, one less because t integral has been done. So now you see, so what are y alpha 1 and y alpha 2? Okay. Let me draw the cylinder again. So this was the cylinder. So this was the direction along which the y alpha was varying, right? So y alpha 1 is essentially the value of y alpha below. Okay. And y alpha 2 is the value of y alpha above. Okay. And the spurious pole was going like this. Okay. So you see that y alpha 1, this circle, okay, or this circle doesn't intersect the spurious pole at all. Okay. So because you have expressed this as a difference between the top and the bottom, okay, and not as a surface integral, okay, this is perfectly finite, free from spurious poles. This is free from spurious poles. Okay. So this is the way we make sense of the integral over the C, over the cylinder. Okay. So let me remind you again that what we had is that we had the integral over this S tilde, which doesn't intersect spurious pole. Okay. Now it may of course hit another loci somewhere, another locus of another spurious pole somewhere, and again one has to do this insert this vertical cylinder. Okay, you have to do it for every one of these. Okay, and so neither S hat nor S tilde had any problem. C had a problem, and now we see that you have resolved that problem by expressing this as a difference between a correlation function on top and a correlation function at the bottom. Okay. Now I should say that the correlation functions at the top and the bottom, these individually, okay, are in the large Hilbert space, because you have a xi without derivative. Okay. So the difference, of course, is a small Hilbert space, but the xi itself is in large Hilbert space. Okay. Fortunately, the Verlinde formula that I mentioned, okay, gives the correlation function in the large Hilbert space. So you can just read out from that formula what it should be. Okay, and it's a perfectly well-defined object, and it has no poles. Are there questions? So this procedure, in fact, can be generalized. Okay, so let me describe this. Okay, so I'll do it in steps. So say, let's suppose that we want to move two PCOs. Okay, here I described that we moved only one PCO, y alpha 1 to y alpha 2. Okay. But you may have reasons why you want to move two PCOs. Okay, and we'll see why we want to do this general case a little later. Okay, but suppose you want to move two PCOs. Okay, so that means that you had two PCOs, y alpha 1 and y beta 1, y alpha 1, y beta 1. Okay, and on top you want to get y alpha 2, y beta 2. Okay. And you want to apply this vertical integration procedure. Okay. So this is the bottom of C. This is the top of C. Okay. It turns out that if you want to get a divergence-free and unambiguous answer, okay, you cannot move them together simultaneously. Okay, we have to do it one by one. Okay. So we have two choices. Okay. We can move first to y alpha 1. Okay, so y alpha 1, y beta 1. We could first take it to y alpha 2, y beta 1. Okay. And then from y alpha 2, y beta 2. Okay. Then each of these steps can be dealt with exactly as I described. Okay, because in each step we are only moving one PCO. Okay, so whatever formalism we used applies here. Okay. Or you can move the other way. Okay, we can move the beta 1 first. and then the alpha. Okay. So these one should be regarded as different sorts of sections. Okay. Now, section I should put in quotes because normally when you have sections don't have vertical segments like this. Okay, so this is a generalized section. Okay, it's some integration cycle in this PGMN. Okay, and the integration cycle has been chosen in such a way that while it does cross spurious pole, okay, we have a well-defined way of making sense of the integral. So moving this way or this way, okay, should be regarded as two different sorts of section, okay, which differ only in their vertical segments. Okay, and just as in the case of bosonic string theory, what we had seen that different sorts of section gives the same result for physical amplitudes. We can show the same thing here. Okay, so these give the same result for physical state amplitudes. Namely, the difference, you can think of this as a total derivative if the external states are physical. Okay, so these are some examples. Now I'm going to try to describe the general procedure for multidimensional integrals. Okay, and when you have multiple PCOs. Okay, what exactly is the algorithm we should follow, right? And how we should organize our calculation. Okay. I'll not describe the full set of steps, but I'll at least give you enough details so that you can from there work out the rest. So general procedure. For integrating over MGMN with typically it will require multiple PCO insertions. So the first step is to divide MGMN into small chambers. Okay, so that the union of those chambers becomes the total MGN. Okay. Now here you can choose a triangulation, but it turns out the triangulation is not the most efficient way to do this. I mean, what the most efficient way is what is called dual triangulation. Okay. But I'm not going to the details, okay, because it's not necessary. Okay, that makes things convenient, but it's not necessary. But let's just say that we divide MGMN into small chambers. Okay, so that collection of those chambers make up the whole MGMN. Then on each chamber, find a section segment avoiding spurious poles. And this is always possible if the chamber is sufficiently small. Okay, so let me represent it pictorially. Okay, imagine that here you have MGMN Okay, this is our PGMN. Okay. And we take some small segment of MGMN. Okay. And imagine that there is a spurious pole locus which goes to PGMN. Okay. And all you are saying is that on this small segment, we erect a section segment, okay, which avoids the spurious pole. Right? And for example, we can put it here. We can put the section segment here. Right? It certainly doesn't hit the spurious pole. Okay. And do it independently on each segment. So on each chamber, we do this. Okay. So we have a next chamber. On this chamber, okay, which is independent section segment. Okay. Say we choose this. Again, avoiding spurious pole. Okay. This also avoids spurious pole. This also avoids spurious pole. But now you see that across the boundary, separating two chambers, PCOs jump. Right? Because clearly this, it doesn't fit continuously. Okay, there is a jump. And the idea is that we'll have to fill the gap using vertical segment. We fill the gap. Okay, so the fact that here you have one set of y alphas and here you have another set of y alphas, okay, you compensate by doing a vertical integration along this, okay, moving the y alphas one by one. Okay, and you can fix a convention. Okay, doesn't matter. Okay. You suppose you decide that you will move the y1 first, then y2, then y3, and so on. Okay, you fix some convention and do this. Okay, it's completely up to you. It doesn't really matter. And you do this for each chamber boundary. Okay, in the next chamber, maybe somewhere here. Okay, the next chamber maybe I shouldn't use green, I use blue again. Next chamber maybe here. Okay. And then we have to again make a vertical jump, okay, to come here. Okay. And again, you have to fill this by using the method of vertical integration. Okay. So this is fine so far. Okay. But the problem is that there may be further mismatch. When these codimension 1 boundaries between the chambers meet on a codimension 2 subspace. Okay. So let me draw this. So suppose you have 3 codimension. So this is chamber 1, this is chamber 2, this is chamber 3. Okay. Let's call this B12, B23, and B31. Okay. And this one is where they meet. Okay, so let's give it a name, C123. Okay. Now, across B12, there are gaps because PCOs are jumping. We fill the gap, okay, by vertical segment. Across B23, the PCOs jump, we fill the gap. Across B31, we fill the gap. Okay. But now, what we'll see is that there can be further additional gaps on C123. Okay. So this may have gaps. That need to be filled. Okay, and I'll illustrate why this happens. Okay, so let's adapt some convention. Okay, let's suppose that there are two PCOs. Take two PCOs. Okay. And let's just adopt the convention that when you go across a boundary, okay, you always move the first one first and then the second one. Okay, that's the way we'll do the vertical. We'll choose the vertical segment. Okay. So then this means that on B12, the way we move is that we start with Y11, Y21. Okay. Then this, you first move Y1, so it becomes Y12, Y21, and then it becomes Y12 and Y22. Okay. So here Y1 is moving, here Y2 is moving. On B23, okay, we start with Y12 and Y22. Okay. You first move this one. So Y13, Y22, sorry. Yeah, Y13, Y22. And then you move the second one, Y13, Y23. Okay. And finally on B31, we start with Y3, 1 and Y3, 2. Okay. You first move this one. So Y11, Y3, 2, and then you move the second one. Okay, so that by the time you have come back, you are back to the original choice PCOs, Y11, Y1. Now let's see why there is a gap. Okay, and for this you have to make a pictorial representation of these movements. Okay, and which is what I'm going to do in the next slide. Okay, but is this clear so far? What I have said? Okay, so let's plot. Okay, this is again a schematic plot, right? Because these are complex numbers, Y1 and Y2. Let's just pretend them to be real and plot it. It doesn't really matter because only the endpoints matter at the end. Right? So this is Y1, Y2 plane. Okay, let's call this the first Y11, Y12. Okay. So across B12, okay, first Y1 moves, then Y2 moves, right? It goes like this, and then it goes like this, reaching some point. Okay, so let's call this point. This will be Y12, Y22. Okay, now we are going to go to B23. Okay, so now this one moves first to 3 and then this one. So let's call this y13, y23. And finally, we have to come back to this point. So first you have to move one. Okay. So we move one. And then like this. So what we see is this gap left over, right? A two-dimensional gap. It looks like a two-dimensional gap, okay, which is okay because this is codimension 2. Okay? This point is codimension 2. Okay? So if you want to make up the full dimension, you need a two-dimensional vertical segment erected on it to make it into the correct dimension that you started with. Okay? So what we see is that on C2, 1, 2, 3, okay, you have left a two-dimensional gap. Okay? So now we have to do a vertical integration, okay, along this surface, not along a line, okay, along this surface, okay, which is two-dimensional. Okay. And basically this integral, okay, let me write this. Okay. So the easiest way to do this is to write this as a sum of two terms, okay, A and B. Okay. So the contribution of A is integral dt1 dt2. Okay. These are the coordinates labeling the vertical directions. Okay. Then dy1 dt1 dy2 okay. So these are just total derivatives. Okay, this is just ddt1 of xi y1 and this is ddt2 of xi y2. Okay, so this integral can be done. Okay, and you can easily see that this will be given by xi of y1 okay. So the y2 moves from 2 to 3. Okay, this the spans from 2 to 3 and the y1 spans all the way from 1 to 3. Okay. Similarly, b can also be done. Okay. A similar integral except the range is different. Okay. And this will give you xi of y1. This goes from y1 to 2, both of these. So y1 2 minus xi of y11 times xi of y2 2 minus xi of y2. Okay, so you have to add these in the integrand and then do the rest of the integral, which is two less dimensional. Okay. Is this clear? Okay. So this procedure basically can be continued. Okay. For the case when you have only two PCOs, it stops at the step that I described. Okay, it stops at this step because now you can show that there will be no further gaps left over, even when this codimension 2 intersections themselves intersect on a codimension 3 subspace. Okay. But if you have 3 or more PCOs, okay, then you have to keep continuing. If you keep continue this process, because there will be further gaps. Okay. And at the end, it gives a fully consistent rules for avoiding spurious poles. Okay. And now the only leftover divergence come from q goes to 0 limit of some plumbing fixture variable. And these, of course, can be dealt with, can be treated using Feynman diagram viewpoint. So let me now give a summary of what you have done so far. Okay, or not really a summary, but some comments. Okay, so what we have is a complete procedure, okay, for computing harmonic superstring amplitudes. Okay, but it's clear that the procedure is complicated. Okay. But it is well defined and finite. Okay. And while for practical computation, okay, we can try to look for simpler approaches. Okay, this makes it clear that the superstring perturbation theory is in principle finite and it exists to all orders in perturbation theory. Okay, we didn't restrict to any given genus or any given number of external states. Okay, and it's written in the form of an algorithm so that it can, in principle, be coded in a computer program. Okay, that's what one means by having a well-defined algorithm, right? Even though if it's complicated. Okay. Now, I should also add that more elegant formalisms may be possible by, say, clever choice of PCO locations, and or local coordinates, and also perhaps supermoduli. As I mentioned, that's the other approach, okay, where you try to keep the world sheet supersymmetry as manifest as possible. Okay. But all this is what for the future. Okay. At present, all we can say is that at least there is a well-defined perturbation theory that exists and it can be used in principle to compute amplitudes to any order in perturbation theory and get a completely finite answer. Okay, so in the rest of the lecture today, I was thinking of working out an example. Okay, not in the full details, but at least I'll give you some idea. But perhaps this is a point I can ask for questions, since there will be no further question answer session today. If you have questions, maybe you can ask first at this stage.
Is it possible to choose a section such that it doesn't intersect this locus of spurious poles?
Okay, I think the answer is not known. Okay, it may be possible, but it's, I mean, nobody has been able to figure out how it may be possible. Okay, what is known for sure is that you cannot choose the section to be holomorphic. Okay, you cannot take the PCO locations, for example, to vary holomorphically with respect to the moduli. Okay, because this follows from some results in the supermoduli space integral, that the supermoduli space is not holomorphically projected beyond certain genus and certain number of punctures. Okay. But whether it is possible to not have holomorphic section, but nevertheless somehow avoid all the spurious poles, that answer is not known.
I see, thank you.
What this construction shows that even if that answer is not known, there's a way to deal with it, even if it's not possible to avoid the spurious poles. Any other questions?
I also have a question. Do you hear me?
Yes. Yes.
Okay. So is it settled that you can systematically separate this kind of spurious singularities from singularities of the boundary of modular space? So there is never the risk that this vertical integration has to be done at the boundary of modular space or something like this.
Yeah. I think that is more or less settled. I think that let me mention that because that's important. Okay. So there are two. So this has to be combined with this choice of S prime Gn, right? So recall that so the freedom that we have is not in choice of SGn, but in S prime Gn. We have is in the choice of S prime Gn, Gmn. Okay. So this avoidance of the spurious poles, etc., that I mentioned, okay, can only be done in S prime Gmn, right? We have no control over the rest of SGmn, which are obtained by plumbing fixture. Okay. But what one can show, okay, and it's not very hard to see this. If we use local coordinates, with large stubs, then plumbing fixture of S prime Gn avoids spurious poles as long as S prime Gmn does. Okay, so you have to make sure that the S prime Gmns avoid spurious poles. Okay, or at least you not avoid spurious pole, but use a vertical integration procedure on S prime Gmn. Okay. And as long as you have made sure that S prime Gmn has that property, okay, one can show that when you sew together these various S prime Gmns to build a full SGmn, okay, you never get any spurious pole. Okay. And essentially it follows from the convergence. Okay. The fact that if you have phi r of 0, phi s of 0, and then phi rc b0 b0 bar, and then either chi 0 or 1 depending on whether it's Raman or Neveu-Schwarz. Okay. So this is multiplied by the integration over the S prime Gmns, which are all finite. Okay, so the only way after plumbing fixture you can get into divergence, okay, is when this sum diverges. Okay, because there is an infinite sum over R and S. Okay, when this sum diverges, then you run into trouble. Okay, and indeed the sum could diverge if you are not careful in choosing the appropriate picture number. Okay, but because we have chosen the picture number to be minus half, or minus 1, okay, we argued that this sum never diverges. Okay, at least for sufficiently large stubs, which means that these fall off sufficiently fast. So that's effectively taking a sufficiently small q. Okay, you get a convergent sum. You never run into any divergence. Okay, and that's what shows that the full answer is finite.
I see. Thanks. This is very nice. Yes.
Yeah. So basically, the idea is, I mean, if you want to ask the spurious poles, so in plumbing fixture, where do they arise? Okay, they arise precisely when you run into this convergence problem. Okay. So as long as you made sure that the convergence problem is absent, you will not get spurious pole from plumbing fixture, as long as they are not present to begin with.
I see. So this original choice of picture is can also be understood as a way to make plumbing's fixture free from spurious singularities.
Exactly. Yeah. Okay. But you also need these large stubs.
Yeah.
So effectively, you want to make Q even though you are taking the Q in the range from 0 to 1, the effective Q you want to make small so that this is convergent, and that requires these large stubs. Okay. So I think if there are no other questions, let me just discuss the example that I wanted to discuss. Okay. So we'll consider a genus 1 2-point function. Genus 1 2-point function of NS sector states. Okay. So the number of PCOs that's needed is 2g minus 2 plus m plus n by 2. So g is equal to 1, n is 0, m is 2, so this is 2. Okay. And the number of moduli that you have to integrate over is 6g minus 6 plus 2 m plus n, and that's 2 times 2, that's 4. Okay, 4 real moduli. So let's start with this. Maybe I'll do it in the next slide, okay, because I need a big slide too. So as usual, you draw the disks. And then you divide. Okay, so the 4 circles are needed in this case. Okay, so you see that this is a disk. This is D1. This is D2. Okay. This is S1, and this is S2. Okay. So the coordinate system will be W1 here. Inside this will be W1. Inside this will be W2. Here it will be Z1, and here it will be Z2. Okay. And let me label the circles. Okay. So C1, C2, C3, C4. Okay. Now, what I'm going to do is to give a slightly different view of this. Okay. So remember, each of these spheres has 3 holes. Okay. But a sphere with 3 holes, I can also represent as a cylinder with 1 hole. Okay. Topologically, it's the same. A cylinder already has 2 holes at the 2 ends, and you just make 1 more hole. Okay. That's the same as sphere with 3 holes. Okay. So let me represent it that way. So we'll represent this as 2 cylinders which will be glued. So we'll think of the left and the right sides being identified. Okay, that's what makes it into cylinder. These two sides are identified. So this will be C1. Okay, so I take orientation this way. This will be C2. Okay, so because you see the S1 and S2, so this is my S1 and this is my S2. Okay, so S1 and S2 join both at C1 as well as at C2. Okay, so that's what we see here. Okay. Then you have the disks. I think I called, let me do the labeling slightly differently. I'll call this S1 and that S2. Okay. This will be my puncture number. This will be puncture number 1. This will be puncture number 2. Okay. So let's now describe various transition functions. Okay. So let's start with C1. Sorry, not C1, C3. Let me draw this. See, this is C3. See, you see C3 encloses puncture number 1, and this is C4. I take this to be anticlockwise. So on C1, sorry, on C3, we have to relate Z1 to W1. Now, clearly by coordinate choice, I can just declare Z1 to be W. Okay. I'll not put any parameter there. On C1, I have to relate Z1 to Z2. Okay, S1 has Z1, this has Z2. So Z1 to Z2. Okay. And I just declare Z1 to be equal to Z2. Because Z2 has not been introduced earlier so far. Okay, I just declared Z1 equal to Z2. On C4, I have to relate Z2 and W2. But now you see that we have already made a choice of Z2, right? I cannot redefine Z2 anymore. Okay. But I could redefine W2, okay, except that the W2 origin is not shifted. That's the rule, right? You cannot redefine W2 by shifting its origin. Okay. So I have to choose, I'll choose Z2 as W2 plus zeta, okay, where zeta is some complex number. And finally, on C2, on C2 again, we see separate sphere 1 and sphere 2. Okay. So Z1 and Z2 have to be related. Okay. And here I have already chosen the relations, one relation between Z1 and Z2. I cannot postulate in further relation. So I'll take Z1 equal to Z2 minus tau. Okay. I could take more complicated relation, but because we are trying to parameterize moduli space, okay, and I should have said here that we are not worried about local coordinates because we will be considering physical amplitudes. Okay, so I have allowed for redefinitions of W1 and W2 keeping their origin fixed. Okay. So at the end of it, what we have got is two complex parameters, and that's enough to label a 4-dimensional moduli space. Okay, so xi and tau, sorry, zeta and tau will label M1, 2, 0. Genus 1, 2 Navier-Stokes punctures, 0 Raman puncture. Okay. Now I have to also specify PCO locations. Okay. Again, we'll choose some particular section. We are not trying to do the most general thing. So let's take the PCO locations. to be the one of them on D1 at Y1 and on D2 at Y2. Okay. So I'm checking the PCO locations. One here and one here. Now I'll leave it and I will take this to be independent of zeta and tau. Okay, I could have made them vary with zeta and tau, but we'll take them to be independent of zeta and tau. Just choice. Zeta and tau by choice, not by necessity. Okay. And so exercise, I'll write down the results in the next slide, but I'll leave it as an exercise to compute b tau bar, b zeta, and b zeta bar. Okay. These can be computed because the transition functions has been specified in terms of as a function of zeta and tau, and the PCO locations have been specified as a function of zeta and tau. That dependence is trivial, of course.
Ashok, question.
Yes.
The choice of putting the PCOs inside the local coordinates of is a free choice, or you're obliged to do this?
No, it's a free choice. I could have put them on Z on S1.
Okay.
Not on S2.
Okay.
Yeah, so that's also a choice. Okay, so exercise. B tau will be given by integral over C2 minus 1 times B of Z1 dZ1. B tau bar be integral over C2 minus 1 B bar Z1 bar dZ1 bar. B zeta will be integral over C4 minus 1 BW2 dW2, and B zeta bar okay. And so the amplitude will be given by sum of our spin structure, which is part of the integration over the moduli space, and integral d tau, which d tau bar, which d zeta, which d zeta bar, and then the matrix element that you have to compute is b tau bar, b zeta bar, chi of y1, chi of y2, and then v1 at w1 equal to 0, and v2 at w2 equal to 0. Okay. Now I'll choose for v1 and v2 some particular form, okay, which is physical state. Okay. So choose vi as c bar, wi, okay, where these wi's are dimensions, sorry, e to the minus. It has to be in the -1 picture, right? So e to the minus phi wi, and this wi will be dimension 1/2, 1 from the anti-holomorphic sector, like del bar x mu, or the g bar a that we introduced, and half from the holomorphic sector, like the psi mu. This should be a mattered superconformal primary. Which means it has to be a primary And if when you take the OP of PF with WI, it should have at most one, a single pole. Okay, it shouldn't have double poles. That's the meaning of a superconformal primary. Okay, so this one in fact can be simplified further. Okay, in many ways. Okay. For example, simplify further. Simplify by taking yi to 0. Okay. We can put the PCOs, okay, on top of the vertex operators. Okay. And here is an exercise. That limit y goes to 0 is finite. Okay. Which I'll call vi0 for now. Okay. So this is a zero picture vertex operator. Okay. This is what people normally refer to as the zero picture vertex operator. Okay. We have emphasized that we are not going to use it. Okay. And indeed, at a fundamental level, we shouldn't use it. But let's just see what happens if we use it. Okay. We just choose, I mean, we have a choice of where to put the PCOs. So let's put them on the vertex operators. Okay. And make them into zero picture vertex operators. So you can make further simplification by moving. Now, see the B zeta and B zeta bar, right? These are integration about C4, right? This is basically integration about the W2 equal to 0 point. So this B zeta bar, okay, you can carry out these integrals by picking up the residues. Okay. So B zeta bar, this again I'll not do, but I'll leave as an exercise. So B zeta bar can be simplified using residue theorem. Effectively, what it's going to do is that it just strips of the V2 out of its C's, okay, and leaves the rest. Okay, and then the chi, of course, goes on top of this e to the minus phi WI already. Okay. So this I'll leave to you to complete. It's straightforward, okay, to do this. Okay. But what I'll end with now is to show that there is a subtlety. Okay. And this subtlety is something which one has to keep in mind, okay, because often there is a tendency to convert the picture of put the picture changing operator on the vertex operator, make them into zero picture vertex operators, and then work with them. Okay, but as you will see now that it doesn't work. Okay, there is a correction that you have to add. Sometimes the corrections may vanish, but it doesn't always vanish. Okay. So what we have done is the following. Okay, so the first PCO is at Z1 equal to T0, right? Because you have Z1 equal to W1 and W1 is 0. Okay. Second one is at W2 equal to 0. Okay. That means and Z2 is W2 plus, so that means Z2 is W2 plus zeta, which is zeta. Okay. And Z1 is Z2, so that's also zeta. Okay, you could also take zeta minus tau, it doesn't matter because there is a tau periodicity in Z1. Okay. So the second one is at Z1 equal to zeta. Okay. So now consider, you have to integrate over zeta. Okay. Consider the limit zeta goes to 0. Okay. So in this limit, the two punctures are coming together. Okay. So one should think of this as a plumbing fixture. Okay. So zeta goes to 0 limit has to be thought of as two things are coming together. So the two vertex operators here, okay, so we glue them together. Okay. So here you have now a V1, in the zero picture. Here you have V2 in the zero picture because you have fused the picture changing operator with the vortex operator. Okay. And now you see you are in trouble. Okay. Because if these are in zero picture, okay, you don't have any more PCOs, right? This doesn't have any more PCOs. So this then necessarily is in -2 picture. Similarly, this is a torus. Okay, total number of picture changing operators should be 0. Okay. That means this must have picture changing this must be in the zero picture. Okay. So the pairing now is becoming between -2 and 0 picture, but this is of course wrong. Okay. We should have -1 picture on each side. So we have done something wrong by fusing the picture changing operators with the vortex operators. Okay. You can do it when they're far away, but it's not a valid operation when they're coming close. Okay. So how do we resolve this? Okay, suppose you like a zero picture vortex operator, right? You want to work with zero picture vortex operator, okay, but you cannot do it everywhere. Okay. So the solution that we can offer is the following. Okay. So let's look at the zeta plane. Okay, let's look at the zeta plane. Okay. So this is the origin. Okay, this is when zeta comes close to this, there is a problem. So what we can do is that we can draw a curve around the origin. Okay, could be close to the origin. This is not in the z plane. This shouldn't be confused with the curves that I was drawing earlier, which was on the Riemann surface. Okay, this is on the zeta plane. Okay, the location of the PCO. Okay, that's the plane we are considering. So you draw a curve. Okay. So as long as zeta is outside the curve, for zeta outside C, we can use the P0s. Okay, so the zeta integral outside can be done with whatever you are using. On C, use a vertical segment. And move the PCO from zeta to zeta naught. Okay, which is some far away point. Okay, so in other words, we had put the chi of zeta, the chi on top of the puncture at zeta. Okay, which are calling z w2 equal to 0 earlier. Okay, but it's a puncture at zeta. We have put the chi on top of zeta. Okay, now on C we have to use a vertical segment to just move the PCO from zeta to zeta naught. Then on C, we have a contribution that is proportional to, okay, inside, okay, V1 remains as it is. And now the vertical integration will give the xi of zeta minus xi of zeta naught, okay, because we are moving the PCO. Okay. V2 becomes in the -1 picture, so that's what I'm calling V2 zeta, and then the B, okay, whatever B you have to insert. Okay, and now this has to be integrated, of course, still. Okay, but the integration will be over d tau bar. Well, there's a B and the b tau bar, all of these are there. So product of P's. Okay. But now instead of having two integrals zeta d zeta bar, okay, you only have integration over this curve. Okay, so if this curve is parameterized by theta, we have only d theta. and we can figure out what the measure is. Okay, because we have given the general form for the measure of a P form. Okay. So on C, we have to add this extra correction. Okay. And inside C, okay, we have to use the usual product of these, okay, and then V10 is still okay. Then V2 of zeta, and then chi of zeta naught. And you integrate. Okay. So inside C, we have to move the PCO. Okay. So you liberate V2, this goes back to the -1 picture. Okay. And you move the chi to some far away point. And now you see there is a problem, because when V10 and V2 come together, if you go back to the previous picture, okay, now this is in the 0 picture, but this has become in the -1 picture. Okay, so now this is in the -1 picture. Okay, and one PCO, that zeta naught, has gone into the torus somewhere. Okay, so this can be in the -1 picture. Okay, so everything becomes fine. Okay. And these corrections are important. Okay, sometimes they may vanish. Okay, but there are examples in string theory where if you don't take into account these corrections, you get the wrong result. So I think this is just an illustration of why these elaborate techniques are useful and necessary. But I think you can do more examples and convince yourself that it is really useful. So I think I'll stop here. Thank you.
So thanks, Ashoke, for these very nice lectures. So we still have time for a few questions, people from online or people here. I have perhaps one more curiosity or questions. This vertical integration procedure where you integrate this exact thing along a vertical segment. So can it be understood as a sort of principal value prescription, or is it something different?
No, it is not actually a principal value prescription. What happens is the following, okay, that because you are integrating del xi, okay, it may have singularities, okay, but the singularities are always double poles. It's a derivative of a function, right? So there may be etas. Okay, let's suppose that it's from the collision. Okay, so you have del xi times eta at some z naught. Okay, so this goes as 1 over z minus z naught square.
Mm-hmm.
Okay, so when you do the integration over z, okay, it doesn't matter which side you go. Whether you go from this side or that side, it gives the same result.
Oh, I see.
So that's why it works. But if you try to vary more than one at a time, right, then there will be some linear terms. And then that will give a single pole and mess up this nice feature. Okay? And that's the reason why you have to always move one at a time. So you can think of this as the integral of a total derivative being given only by the boundary terms. But in terms of singularities, what's happening is that the poles are always double poles. And because they are double poles, you can integrate around them. It's unambiguous how to integrate around them.
Okay, now I understand. Thanks. So if there are no other questions, I think we can take Ashoke again. And